All right, this week we're going to be thinking about and engaging in a discussion about modeling shape, and ultimately this comes back to mathematics, where we learn the elements of geometry, which interestingly enough is sort of ancient mathematics. All mathematics was geometry at one point, and then later mathematics was enriched by other subfields. So we're going to begin with a picture of a set of models that came from the inside of an ancient Egyptian tomb. So these are very common models, actually. If you go to the Egyptian section of a museum, you may well find these funerary models, which were placed inside the tomb of an important person that's buried there. And the models played a key role in the afterlife. Now, in this particular case, the material is wood. And so a lot of these models that went inside of, were placed inside of tombs were painted wood. They're wood cut up and then painted. But so you're looking at things that are 2,000 to 3,000 years old or more. And so modeling certainly began there, and of course before, but this is a kind of a good place to begin. The idea of physically modeling at scale. Another scale model is from the sculptor Bernini, who's an artist, a sculptor that was exhibited throughout the US, maybe throughout the world. There's a particular link, all these things are hyperlinked, and there's a particular link to the Met Museum in New York City. But I've also included a link when it was at the Kimball Museum in Fort Worth. I remember because I went to that show on the Bernini terracotta models. So essentially you're looking at earth and clay models that were meant to be models for a sculpture that was etched in another material like stone or marble, for example. So again, here we're kind of thinking about modeling as being physical, just like it was for the ancient Egyptians. But we all grew up with these kinds of things. I don't know what you used. It kind of depends on when you grew up and what was popular. Play-Doh, I remember playing with that. Lego is still very popular. Some of these things have sort of lost their edge a little bit. Lego is still extremely popular. Play-Doh, probably. Lincoln Logs, I don't know. I used to play with Lincoln Logs. Now, a couple things to think about when you're looking at materials like this that kids use to make models is that some of these modeling kits are so generic that you could pretty much create anything you want. Whereas other kits are object specific or scene specific. So these two down here, for example, this is Meccano, which has been around a long time. And it looks like you can make vehicles. And this particular kit, you could make what you see here. This is what is made from the kit. And the kit will, of course, include all the component parts. And you put it together. That's a little different than something like Play-Doh or Lego, where the component parts can really be combined together to create many different objects. And Tinker Toy, what could be, we can't really talk about modeling without Tinker Toy. It's been around a while. Each of these materials has its own benefits and characteristics, and this is true of all modeling. It's very material specific when you're dealing with physical modeling. Now, just some early stuff. I'm not going to go into detail about the first jobs that I had, but I worked at this place for about 3 years, and they did a lot of modeling because they were building things like this ship right here, which looks to be an aircraft, the beginnings of an aircraft carrier. So Newport News Shipbuilding would produce a lot of things for the Navy, including nuclear-powered carriers and submarines. Now, my first job was in computer-aided design, computer-aided manufacturing. That's what these acronyms mean. And I mostly worked on the programmatic end of that. That is, what was needed to write computer programs that would assist the engineers and the designers in making models for things like this ship. Now, this is an example of what would be used today. Back in the Stone Age, when I was doing modeling, it was very, very primitive. Today you would have a ship model like this with a lot of subsystems. HVAC, piping, power, electronics. Right? All of this stuff has to be modeled if you want to create a 2D and 3D representation of it. So now we're gonna do is we're kind of gonna move more towards the mathematical and especially the digital modeling. We're going to use the computer. Again, before the computer, people use all kinds of materials, and they still use materials to do modeling, especially artists. All right, so this kind of modeling is different than some of the other kinds of models that we'll talk about in the class. This kind of modeling is used when you want to create something that visually represents its target, like you did with Legos and Play-Doh. Right? You want to make something that looks like something else, but it's easier to work with, and so it's a simplified representation. Now, there's lots of modeling languages. You can use everything from a programming language, using a library like OpenGL, or you can use tools like visual interfaces like SketchUp. There's literally hundreds, if not thousands, of packages that you could use. Modeling can be procedural, in which case you specify a process or procedure, and if you do that, you will end up constructing the final model. Or it can be non-procedural. Think about this as kind of being interactive without a memory. Procedural naturally has a memory because the procedure has to be written or drawn. Now, we kind of started our digital understanding through mathematics in terms of knowing what geometry is. And that's pretty much essential. So everything you learned in geometry in school is relevant here. And I'm not going to go over each of these links, but I've linked a few things together that's a recap of what you learned mostly in K to 12. In university, there's different sorts of courses that deal with modeling, and it all depends on a modeling of the type we're talking about. Depends on what building you're in. Things like non-Euclidean geometry would be taught in mathematics and physics, in topology in terms of mathematics. So a key thing that's important with modeling is what's the context. And this is kind of like the question of what building are you in when you ask, hey, what modeling do you do? If you're like me and you work, if you happen to work in a CAD/CAM modeling position where you're modeling a helicopter, a Tesla automobile, or an aircraft carrier, then you're working in computer-aided design, which is different in different kinds of models than if your purpose is to create an animation, either in 2D or 3D. If you're creating something for cinema, for example, you will use a certain kind of model. If you use games, you may use another kind of model. One of the differences, of course, between games and animation is the games are interactive, generally speaking. In animation, unless you can have interactive animation, but basic animation is where you consume by watching your TV or your screen. And of course, there's design. Many designers just work in 2 dimensions. Okay, this just has to be remembered with modeling. So, I mean, there's the 2D modeling. If you draw a circle or a point or a square or a rectangle, you're dealing with 2D. 3D takes that into another dimension. If you're working in the engineering school, the engineers, depending on what they're working on, we use specific sorts of models. Often finite element or finite element models. So what kinds of geometry? Well, I'm going to be going over some real basic types. And these can get into more detail, but I think this will suffice for now. Point cloud is something that has been relatively recently very useful. And what you have here is literally a cloud of points. You got a whole bunch of points, and that's your model. Now, clearly, the points by themselves may not be that useful, and the question is, how did you get those points? Well, you can get them through different technologies. There's mesh models. Earlier, these were called wireframe, not to be confused with wireframe in UX design. Completely different concept. Constructive solid geometry, CSG, curve and surface. And here you have curves like Bezier curve. Now, if you want to take simpler curves, you might have a circular arc or a straight line segment. Cell-based and procedural. So we'll go over examples of these. Point cloud is kind of interesting, especially because, the Apple iPhone 12, for instance, came out and contains a LiDAR sensor, which creates it basically determines range from a particular point where the sensor is located on the phone. Now, before that, of course, you could buy LiDAR instruments, and you could go around and get a cloud of points from those instruments. But it's just interesting that it's come to the point where consumers that have smartphones can enjoy LiDAR. Photogrammetry is also another classic method, because what you do is you end up with a bunch of points that are in places in multiple images, which are all images of the same thing, but at different angles. So photogrammetry is a reconstructive effort. Okay, in terms of mesh, it's sort of what it sounds like. Here's a torus, or if you like, a donut. Here is a plane. Here's a cube. Here's a cylinder, and so forth. Here's a funny picture of a monkey head. This is the mascot, if you will, the digital mascot of Blender, which is a free, open source package for doing 3D modeling. But mesh is what it sounds like. It's carved up into a bunch of primitives, like little teeny rectangles or little teeny triangles. There's another area called constructive solid geometry, and I'll go over some simple examples of this. But again, most of these slides, if you click on these, you'll find the reference for what I'm talking about, and it'll go over it in more detail. So here's an example of constructive solid geometry. Generally, what you're taking is logical Boolean operations, Yes, these are the same Boolean operations that if you create a computer program, you say this and this or that and so on. So in this particular case, this is a difference operator because it looks like a minus sign. This is a union operator. So they're set theoretic in this. They're like operations that you do in set theory. But if you want to create a coffee cup or a mug, how do you do it? Oh, we take a handle and we combine that. That is, we union that with a cylinder. How did we create the cylinder? We subtracted a smaller cylinder from the larger cylinder. So this CSG creates a kind of a tree of operators. Here's another example. And you can either start at the top, which is the final object, or you could start at the constituent primitive outer layer. These are the leaves of the tree. And you can work your way up using the operators. Curves and surfaces. These are examples of parametric curves, like typically a spline. We're based on this. The curve itself is this blue curve. That's the spline. And these little green dots right here are control points. So this is almost like what a marionette, a kind of a marionette sort of scenario. You pull or push on these green dots and it will change the shape. Now again, before everything, all of these things have pre-digital analogs. Designers and mechanical engineers and so on, they used to use physical splines, which you can still buy. And they are these kind of rubber-coated metal tools that you can buy. You can kind of shape it, almost like you would do in Play-Doh or something, but you can shape it and you can make the curves almost anything you want by just physically moving it around. And that's what people used before the era of the computer. These are control points for a surface. So you can have control points for curves or for surfaces. Now, of course, procedural modeling, different ways of doing that. One classic way is to use a computer programming language. This is part of a tutorial on how to make a sphere using OpenGL. And so this is a language, this uses OpenGL and is a programming language. Virtually all programming languages have graphics libraries, and you can make geometric constructions through those languages. One classic one that is used in the design area is called processing. And processing is a family of languages, including JavaScript, Java, Python, and so on. So yes, you can actually create stuff by defining the process by which the thing is created. This is a digital method for doing that. This is a composite image. It's got different things in it. The actual procedurally generated model is this diagram right here. And I'll show another example in the next slide. Now, interestingly enough, this is also a model. It's just not a geometry model. It's a data flow model that, when executed, produces a mesh. So this is the output. And if you want, you can call this the program, or you can call it the data flow model. It's a different kind of model that we'll talk about later. And so process model, data flow model, whatever you want to call it. And this package that uses this is out of part of Rhino, and it's called Grasshopper. And it's for computer-aided design. So a good point, this is actually a good point to talk about the difference between design and non-design modeling. Often when you see CAD, computer-aided design, what it's doing is referring to modeling that is situated in terms of units of measure, like inches, millimeters, meters, feet, yards, whatever. And so what happens in CAD is these are precise. What you're looking at digitally also has a unit of physical measure associated with it. Why is that useful? Well, if you're making an aircraft carrier, everything has got to be correct in terms of its length and its volume and so forth. Now, if you're making a game or you're making something for cinema, an animation, you may not care about that. It doesn't matter how many inches it is or cubic feet it is, right? And so it's just worth knowing that depending on where you go and hang out, some people use this if they're dealing with reality. And the animators and gamers are not necessarily dealing with modeling reality. They're modeling something that's often fictional. This is just another picture of grasshopper model. So the way this works is that these are some sliders. These will produce numbers. So this is interactive, and you move it left to right, it will produce a different number. That number then goes out and bifurcates right here. So it goes here into this port of this object, and it also goes here into this port of this object. And these objects are sometimes called nodes or functions. It kind of just depends on the language that you're working with. So again, Grasshopper is procedural. Maya is a production industrial product, but we also use it at the university. And there are these are procedural. It's why I'm calling about procedure here. So this is a procedure that allows you to create these nodes. That's these things that are rectangular. And then, like Grasshopper, to take outputs from one node and put them as inputs to another node. Again, you click on these things, you'll get into more detail for that. This is the same thing for shading. Same abstract structure, nodes, arrows. Kind of getting back to the aircraft carrier and shipbuilding and so on, it's interesting to note that you can kind of have a model of modeling, if you will, which is to say, if you wanted to create a ship, you need to start your modeling using design kinds of models. And then you have to start considering the arrangement of the space, the structure. This is where the civil engineers come in finite element modeling. You have to think about the materials that are being used. All of the routing for HVAC and piping have to be considered, as well as the routing for your electronics and your electrical wiring. So each of these phases has geometry associated with it. It's just that this is this is put in my procedural discussion because this is a procedure. This is a kind of a macro procedure for making objects and putting them all together in a final product. Now, I'm going to talk about this in a separate video, kind of the next video I'll record. And these are free modeling tools, so you get some kind of experience in modeling. Modeling is sort of a lifetime passion, and there are many courses on each kind of modeling that I've talked about. But I'll be going over these in another video.